evening to everybody. Today you are going to study about multivibrators. At the end of this lecture class, you can understand about the objectives, what is a multivibrator, types of multivibrators, circuit operation of bistable multivibrator, monostable multivibrator, astable multivibrator, and finally the working of split trigger. Now we can see these objectives one by one. So first thing is, what is a multivibrator? Multivibrator is an electronic circuit which generates non-sinusoidal waves such as square, sawtooth and triangular waves. As we know, most of the oscillators generate sinusoidal waveforms. So we can consider multivibrator is an oscillator that can generate non-sinusoidal waveforms. The inverter circuit is the practical form of the transistor switch. That is the basic circuit which is employed in all forms of multivibrator circuits. So every multivibrator circuit consists of an inverter, which is nothing but a transistor which is operated as a switch. So this is the circuit which explains about the operation of a transistor as on switch and off switch. We know that the transistor can operate in three different regions, that is in active region, saturation region and cutoff region. When it is operated in saturation region, it can be used as that is when it is using in active region, the transistor can be used as an amplifier or as an oscillator. Whereas when it is in saturation or in cutoff regions, its application is as on switch and off switch respectively. So here, when the base emitter junction, that is the input junction of a common emitter transistor is forward biased, and if this forward bias is sufficiently large, then the transistor will be driven into saturation. So when the transistor is in saturation, the collector current of the circuit is controlled by the load resistor RL, because the collector to emitter junction of the transistor acts as a short circuit, as its resistance across this junction collector to emitter is 0. So with this, the drop across this collector to emitter junction is equal to 0. So for an on switch, the transistor output Vc is equal to 0. If you go for the transistor whose input junction is reverse biased, then this mode, the transistor will act as off switch. This is because we know that in a transistor, the base current controls the collector current, and with the relation IC is equal to beta IB. If you make the input junction, that is emitter to base junction of a transistor reverse bias, then the base current here will be reverse leakage current, which may be 0 for a ideal case. So when base current is 0, automatically the collector current will be 0 according to this equation IC is equal to beta IB. So whenever IC is equal to 0, so as you know from the transistor equation, VCC is equal to ICRL plus VCE, we can see that VCE is equal to VCC with IC is equal to 0. So that means the collector to emitter junction of the transistor with IC is equal to 0 will be equal to the entire applied voltage VCC. That means it acts as a open circuit. So it resembles an off switch. So we can conclude that a transistor, when it is forward biased at its input junction, will act as on switch, and when the input junction is reverse biased sufficiently, then it will act as off switch. So here you can see the transistor switch with input applied with some negative bias for certain period and positive bias for a certain interval. Whenever the input junction is reverse biased, the collector current or the base current, which indirectly reflects the collector current, is equal to 0. So when IC is equal to 0, the output voltage VCE is equal to VCC. So this is output of an off transistor. Here we can see in this time interval, the input applied to the input junction or to the emitter base junction of the transistor is such that to forward bias the junction and is sufficient to drive the transistor into saturation. Hence the transistor can draw large current which equals to IC sat, that is equal to VCC by RL, and thereby the output voltage VC is equal to 0. So for an on transistor the output is 0. For an off transistor the output voltage across collector to emitter junction of a transistor VCE is equal to VCC. Now we can see the basic block diagram of a a multivibrator circuit. A multivibrator circuit consists of two stages of common emitter amplifiers which are coupled such that the output of each is connected to the input of other stage and vice versa, and these two stages are coupled by some coupling network. Generally RC coupled network is going to be used, and we know that in a common emitter configuration the transistor output is 180 degrees phase inverted with that of the input signal. Here we can see the signal which is fed to each of the stages will pass through two stages of common emitter amplifiers. That means the signal will suffer or undergoes twice 180 degrees phase inversion. Thereby the resultant signal which is fed to the input of each stage will undergo 360 degrees inversion. That means it will be in phase with the input signal. Hence the feedback here will be positive feedback. And one more thing here is the feedback signal amplitude will be so large such that the transistors in these circuits can be switched from on to off states or off to on state instantaneously. That means the amount of feedback is very large so that the transition can occur within no time. Now we can see a multivibrator states. So a multivibrator can have two states. That means the output of multivibrator can exist in two different states. So let us say the first state how the multivibrator can have its output is T1 is equal to on, that is the transistor T1 is in on state, and at the same instant transistor T2 will be off. So this is one state how the multivibrator can have its output. And if you go for the next state, that how the multivibrator can have its output is the transistor T2 is on and the transistor T1 is off. So this is how the multivibrator circuit can have two states. Accordingly, how the transistor is going to changes its states, that is from first state to second state or from second state to first state, the multivibrators can be classified into three categories. So the classification depends on how the stages will change or how the output changes from one state to another. Accordingly, we have bistable multivibrator or flip-flop, monostable multivibrator or one-shot multivibrator, stable multivibrator or free running multivibrator. Now we can see about these multivibrators one after another. Let us start with bistable multivibrator. Bistable multivibrator is an electronic circuit which has two stable states, and the circuit can remain in each of these stable states for indefinitely. That means it can change its state only if we apply an external trigger signal, which may be voltage or some external force to the circuit. So bistable multivibrator can retain in its stable state any of the stable states unless we make it to do by applying an external trigger voltage to the on transistor. To study about how the bistable multivibrator can have transition from one stable state to another stable state. Let us trace its circuit operation. This is a bistable multivibrator circuit. As we have already known that the bistable multivibrator has two inverter circuits. This is first inverter circuit and this one is second one, and the output of each stage is connected to the input of another stage. So let us say initially the transistor T1 is in off state, that is at cutoff, and transistor T2 is on state, that is at saturation. As we know, for an off transistor, the output at collector terminal of the transistor is equal to VCC, which will be input to the base of transistor T2. So this VCC is available at this point, where minus VBB is here. So the potential divider R1 R2 can provide the sufficient positive voltage at this point so as to forward bias this base interjunction, because VCC is very large compared to that of VBB, even though it is minus, and the voltage at this point is plus VCC. Hence the voltage that is applied to the base interjunction will be positive, and it is sufficient to drive the transistor into on state. And for a on transistor, the output V02, which is input to the first stage V input 1, is equal to 0. So this 0 volts is available at this point with no input signal. Here the potential divider R1 R2 in conjunction with the minus VBB can provide a negative voltage at the base of T1, and hence the base interjunction will be reverse biased. So this reverse bias voltage will keep transistor T1 in off state. So the state of T1 is off, and with this VCC where T2 is on will be maintained or will be continued indefinitely until we want to make it to disturb by applying some external trigger to the on transistor. In this case here T2 is on transistor. So let us apply a momentary short across base emitter junction of this transistor T2, or some negative going pulse at the base emitter junction of transistor T2, so that forcefully to drive the transistor T2, which is in on state, into off state. With transistor T2 made into off by applying a momentary short across base emitter junction, can have an output is equal to VCC. So this VCC will be applied to the input of transistor T1. So here it will be VCC and this is minus VBB. As previously discussed, the potential divider R1 R2 can provide a positive bias to the base emitter junction of T1 so as to make it to be on, and on with T1 on, the output will be 0, and which will provide the necessary reverse bias, or which will keep the reverse bias voltage across transistor T2 and held the transistor T2 in off state. So this state of T1 is on and T2 is off will further maintain indefinitely unless we apply some external trigger to the transistor T1, which is now in on state. So that's why the bistable multivibrator can remain in one of its stable states indefinitely until we disturb it or until we make it to change its state by applying some external signal. So let us see, this is the output waveform how the bistable multivibrator can have by applying some external trigger to the on transistor. So initially let us see VC1, which is off transistor we considered, is equal to VCC, and at the same time the transistor T2 is in on state and it equals to 0. So at that time a negative going pulse is applied to the on transistor T2. So with this negative excursion pulse, transistor T1 will be switched on and simultaneously transistor T2 will be switched off. So this transition we can observe here. The transistor T1, which is previously off, will enter into on state, thereby output will be 0. Whereas the transistor T2 whose output is 0, which is in on state, will now switch on to the off state. So this is how the bistable multivibrator changes its state of stable 1 by applying some external signal. Thereby we can conclude that bistable multivibrator is an electronic circuit which has two stable states. Because we are naming them as stable states, because in each state it can remain. If we don't modulate it will be continued in the same state. So it is called as a stable state. To change these stable states, always we have to apply an external trigger pulse, and it has only two states which are both of which are stable. That's why the name bistable multivibrator justifies it. Now we can discuss or we can go for the next type of multivibrator, that is monostable multivibrator. Monostable multivibrator is an electronic circuit which has again two states, but among these two states one is a stable state and another one is a semi-stable state or quasi-stable state. So here the monostable multivibrator can remain in its stable state until we apply some external signal, as in the case of bistable multivibrator just we discussed now. So when we apply some external signal, then the multivibrator, that is monostable multivibrator, can switches into another state, and within this second state it can remain only for a fixed interval of time, and this time interval is decided by the time constant elements such as R and C used in the circuit. After the lapse of this time interval, the monostable multivibrator output can switches back into its stable state. That's why the second state in which the multivibrator can remain only for a fixed interval of time is called as semi-stable state or quasi-stable state. For example, the multivibrator is in its stable state with T1 is equal to off and T2 is equal to on. Let me think. Then it will continue in this stable state of transistor T1 off and T2 on indefinitely. If you make it to change its state by applying some external trigger, then it can enter into another state, that is transistor T1 is on and transistor T2 is off. Within this state, the transistor can retain only for a fixed time interval of time. After the completion of this time interval, the output changes back into its stable state and retain in that state indefinitely. That's why a monostable multivibrator can have one stable state and one semi-stable state or quasi-stable state. So let us trace the circuit operation of monostable multivibrator, how it is going to change its states from stable state to semi-stable state. This is a monostable multivibrator circuit. Once again, it has two inverter circuits with transistor T1 and transistor T2 in each of the circuits, and the output of each is fed to the input of another one. Here T1 output at the collector terminal is fed to the base of T2. Similarly, the collector output of transistor T2 is fed to the base of T1. So let us assume initially transistor T1 is in off state and transistor T2 is in on state. We start with this assumption. As we know, for off transistor, collector voltage is equal to VCC. For an on transistor, collector voltage is equal to 0. So at this point the available voltage is VCC, hence the capacitor can charge towards VCC with the polarity plus this side and minus this end. And here the resistor can provide a negative bias that is sufficient to keep the transistor T1 in off state with this minus VBB. As we have seen, this transistor T2 is on, VCC will be available here, isn't it? So VCC is this is on transistor, this one is 0 volts. 0 volts is available at this point where it is negative minus VBB, hence the base to emitter voltage is a reverse bias voltage which keeps transistor T1 in off state. So here transistor T2 is on, whereby the voltage is 0, which is input to the transistor T1, and in conjunction with that here we are having some minus VBB which keeps the transistor base emitter junction in reverse bias condition, hence transistor T will be held in off state. As it is in off state, it can be charged to VCC, and which is the charging current will be the input current to the transistor T2, hence the transistor T2 will be maintained in on state. This state of transistor T1 off and transistor T2 on is continued indefinitely, hence it is a stable state. To change its stable state, we have to apply a negative trigger pulse to the base emitter junction of on transistor. If we apply a negative trigger pulse, then the base emitter junction will be reverse biased, so T2 will be driven into cutoff region, so it will be off. For an off transistor, the collector voltage will be equal to VCC, thereby this VCC will be available to the input of transistor T1, hence the base emitter junction is going to be forward biased. So the condition of T1 will be changed to on state. With T1 on, the voltage available at this point will be 0. So now the capacitor which is previously charged to plus VCC with this polarity can be connected to the ground with the plus polarity of the capacitor effectively connected to the ground through this on transistor T1 on. So now T2 is off, T1 is on. When T1 is on, the charged capacitor plus terminal is effectively grounded. Now the capacitor can charge towards plus VCC through OR and the short circuit across collector emitter junction. So the capacitor now charging from minus VCC towards plus VCC. So here the charging path is shown here. So the capacitor is charging from minus VCC to plus VCC. So this charging voltage or the charging current will be the input current to the transistor T2. So as T2 which is in off state will have a charge which is changing from minus VCC to plus VCC. So when the capacitor charged to 0 volts, the transistor T2 will get a positive bias and the transistor T2 will change its state again back to on. So we can see the transistor T1 is on and T2 is off. State can be maintained only for a fixed time interval T, which is the charging time period for capacitor C through OR up to minus VCC to 0 volts. So when the capacitor charges to 0 volts, the base emitter junction will be forward biased, transistor T2 will be on, and automatically when it is on, it is 0 volts, which will cause transistor T1 to have negative bias across its input and it will be forcibly switched off. So this condition of T1 off and T2 on will further be continued until we apply another trigger pulse, which is negative going pulse, to the base of transistor T2. So this is stable state, whereas another state where T1 is on and T2 is off will be held only for a fixed interval of time decided by this time constant elements R and C. Thereby T1 is on and T2 is off is semi-stable state. Here we can see the output waveform of a monostable multivibrator. This is at the collector of transistor T2, this waveform at the base of transistor T2, this is the output of transistor T1 at its collector, and this one is the voltage at the base of transistor T1. So here a negative going pulse is applied to the base of transistor T2. So whenever we apply a negative going pulse to the on transistor T2, which is changes its state from on to off. At the same time, the output of first transistor changes from off to on, and this one is the input voltage to the base. So here we can clearly see it will be forward biased for the time during which transistor T2 is on. After that, with the negative trigger pulse applied to the base, the base voltage is having a negative excursion. With this, the transistor T2 will be switched off and T1 will be on. As T1 is on, the capacitor will charges from minus VCC to 0 volts. This charging voltage will be the base voltage of transistor T2. So this is the capacitor charging voltage, which is nothing but the base voltage of T2. When the capacitor charges to 0 volts, automatically it will enter into forward bias region, and hence the transistor T2 will be on. So this is the time period during which the multivibrator can remain in its semi-stable state. This is just inversion of T2 outputs, because whenever T2 is on, T1 will be off, and T2 is off, T1 will be on, and accordingly the base voltage will also be inversion of the base current of transistor T2. So we can conclude bistable multivibrator has two stable states where it can be delayed in its quasi-stable state for a fixed interval of time to change its state into stable state. Hence it is called as a delay circuit. So the monostable multivibrator will retain in its stable state indefinitely. Once we apply some trigger pulse, it can enter into semi-stable state, and how much time it can stay in this stable state, semi-stable state, can be decided by the time transient elements. So that's why how much time it can be delayed will be decided by the elements. So it is called as delay circuit also. So the negative going output of the circuit occurs only after the completed interval of semi-stable state. So that's why the monostable multivibrator output is a rectangular one, which is frequently used to control the other circuits. So it is also called as gating circuit. So it's a delay circuit as well as gating circuit. Now we can go for another multivibrator, the third type, which is astable multivibrator. Astable multivibrator is an electronic circuit which has two states where both of the states are semi-stable states. As we stood from the monostable multivibrator, semi-stable state means it can retain, the output can retain in this state only for fixed interval of time. So here the astable multivibrator has both the states which are quasi. That means the multivibrator can retain in each of its state for a fixed interval of time decided by the circuit elements. So the duration of each semi-stable state will be decided by the transients RC used in the circuit. Let me see the circuit operation of bistable multivibrator. Here this is the bistable multivibrator. We can see here C2 RB2 will constitute one time period, that is a time period elements, whereas RB1 and C1 will constitute another time period for another state of semi-stable. So as usual, let us assume with the condition that T1 is in off state and T2 is in on state. When T1 is in off state, its collector voltage is equal to VCC, and the capacitor C2 can charge to VCC with this polarity as indicated here. So here the RB2 is so selected to provide the sufficient negative bias to the transistor T2 whenever T2 is in cutoff. Similarly, RB1 is selected such that it can provide the minimum value that is necessary to hold the transistor T1 in on state whenever it is on. So here transistor T2, when it is off state, the capacitor C1 can charge with the voltage VCC available when T2 is off. So T1 will be off, C2 is charged with this polarity towards VCC. When T2 is off, C1 can be charged to VCC with polarity shown here. So let us see the condition. First condition, T1 is off and T2 is on. When T2 is on, the capacitor C1, which is charged to plus VCC, whose positive plate is effectively grounded through transistor T2 on. You can see here. So T2 is on and T1 is off. So the capacitor C1 through this RB1 can be grounded to T2. So this is the VCC, RB1, C1 and on transistor T2. Here the capacitor has minus polarity, plus polarity, which is charged to VCC previously. So now the capacitor finds a path to charge towards plus VCC, as in case of monostable multivibrator, which we have just discussed, through this RB1 and T2. So here the capacitor is charging from minus VCC to plus VCC. Thereby the charging voltage of the capacitor will be the base voltage to the transistor. The charging voltage across this capacitor, because it is a short circuit, so the charging voltage across capacitor will be the base to emitter voltage of transistor T1. Clearly we can see here the charging voltage of the capacitor is increasing towards VCC. So whenever it reaches 0, automatically just by crossing 0, the transistor T1 base emitter junction is going to be forward biased. So whenever it is forward biased, the state will be changed. T1 will be on and T2 will be automatically switched off. So the time duration, how much time T1 will be off and T2 will be on, will be decided by RB1 C1. So when T1 is on and T2 is off, once again this state will be remained only for a particular interval of time, because here now with T1 on, the capacitor C2 can be grounded effectively through transistor T1. So the plus terminal of the capacitor is going to be grounded effectively through the short circuited transistor T1. So further, the charging voltage across the capacitor will be the input voltage to the transistor T2, as previously explained. So here whenever C2 charge reaches from minus VCC to 0, that is depending upon the time constant RB to C2, it can enter into forward biased mode. Thereby once again transistor T2 will be on and T1 will be off. So here we can see here the output of first transistor VC1, input voltage of first transistor VB1, output voltage of second transistor VC2 and input voltage of second transistor VB2. Clearly we can see whenever the transistor T1 is in off state, transistor T2 will be on state, and its transition, during the transition the charging across the capacitor will be the input voltage to the transistor T1. So whenever it changes from reverse bias to forward bias, it can change from on state to off state. So that's why we can see the astable multivibrator can generate a square wave whose amplitude is given by the equation VCC minus VCE sat. So the amplitude of the waveform is equal to the applied voltage VCC minus VCE sat, that is saturation voltage, and the time period of this output voltage is given by T is equal to 0.69 RB1 C1. This is first time period provided by this RB1 and C1 elements, and 0.69 RB2 C2. So the sum of these two will provide the time period. If If you take RB1 is equal to RB2 is equal to R, then the output of the astable multivibrator can have a time period T is equal to 0.69 or into C1 plus C2. So we can conclude the astable multivibrator is a square wave generator which can generate the square wave very freely without the need of any applied trigger pulse. And we can go for the last circuit, which is Schmitt trigger. Schmitt trigger is nothing but a special form of bistable multivibrator, which is an emitter coupled bistable multivibrator. We know in bistable multivibrator, which has two stable states, changes from one stable state to another stable state at the instant where we are going to apply a negative trigger pulse to the on transistor. That means the rate at which the output of the bistable multivibrator is going to change depends upon the rate at which we are applying negative trigger pulses to the on transistors. Whereas in case of Schmitt trigger, the change of these states will be decided by the input signal. If two finite values on the applied input signal will make the circuit to change from one stable state to another stable state. So Schmitt trigger is nothing but a bistable multivibrator. The only difference is in bistable multivibrator we are going to apply a trigger pulse, whereas in case of Schmitt trigger we are going to apply an input signal whose amplitude is going to decide at 2 points to change its state. So the two finite values of input voltage cause the circuit to switch from one stable state to another stable state. Let us see, this is the circuit of a Schmitt trigger. So initially, without applying this input signal, let us consider T1 is off and T2 is on with no input signal applied. So T1 is on and T1 is off and T2 is on. When T1 is on, it is a short circuit and there will be some voltage drop across this emitter resistor RE. So let us name it as VE or VE2. So this VE2 is available at the emitter of transistor T1 and there is no signal at the base initially. So here it is 0 and this is plus VE2. So if it is 0 volts and this one is plus VE2, then the base emitter junction is reverse biased. Then T1 will be in off state. So at this time, let us apply some input signal, which is a sinusoidal wave as shown here. It is a positive going sinusoidal signal. That means the voltage at the base of this transistor T1 is gradually increasing. So when it is increasing and attains a value which is just greater than VE2, which is available at the emitter of T1, that is the drop across this emitter resistor, then the base emitter junction will be forward biased. So the voltage at which the transistor T1 can be switched on is called as upper triggering point. So upper triggering point means VET plus V gamma. It is the amplitude that is necessary at the input voltage which causes the transistors to change their state. So VET is voltage drop across RE when transistor T2 is on, and V gamma is that is the cut-in voltage that is necessary to forward bias any diode. So here when the input voltage reaches this upper triggering point, then T1 will be on, which is previously off, and automatically whose output will be input to the transistor T2 will be off. So this state will be continued until the input signal reaches a value which is less than this upper triggering point. So when the input voltage becomes less than this upper triggering point, which is called as lower triggering point, when it reaches this value, once again transistor T1 will be switched off and automatically transistor T2 will be switched on. So this transition at which it takes place is called as lower triggering point. Thereby the two finite values on the amplitude of input voltage will decide how the output of Smith trigger is going to be changed from on to off and once again to on. So the rate at which it happens will be decided by the amplitude of the input signal finite values. Excuse me. And now we can conclude the Smith trigger is a square wave generator whose frequency depends upon the applied input signal. If we compare with bistable multivibrator, the frequency depends in bistable multivibrator about the rate at which trigger pulse is applied. Here astable multivibrator is also a square wave generator, and if you compare Smith trigger and astable multivibrator, both are square wave generators, but in astable multivibrator the square wave is produced without applying any input signal, whereas in case of Smith trigger we need an input signal which is a sinusoidal wave, and the amplitude levels, two different amplitude levels will decide the Smith trigger output to change. So we can conclude the Smith trigger is a special form of intercoupled bistable multivibrator, and we can have a square wave output from this Smith trigger, and also astable is also a square wave generator, monostable is also a square wave generator, bistable can also produce a rectangular or a square wave generator, but in all these four cases we can see how the generation of rectangular wave or square wave is going to be happened. In bistable we need trigger pulse to each of the transistors to change their states, whereas in monostable multivibrator we need only one trigger pulse to change to have the entire time period, whereas in astable no need of a signal. So that's why bistable is called as a flip-flop, that means it can be used as a storage device, whereas monostable, as it needs one trigger pulse to have entire or one period of operation or one cycle of operation, it needs one trigger pulse, hence it is called as one shot. Whereas on the other side astable doesn't need any trigger pulse for its operation, hence it is going to be free running multivibrator, whereas Smith trigger is also a square wave generator which is used to differentiate two amplitude levels also. So it is also called as the comparator, the amplitude comparator. So with this we can conclude multivibrator can have a stable state or a semi-stable state, based on which we can classify them into different types. Thank you very much.